In this video, we'll see how to convert multiple analog signals to digital with the MSP430 microcontroller. In the first setup, we'll use 6 potentiometers for creating variable analog signals, and in the second setup, we'll be replacing 2 potentiometers with an analog joystick. After understanding related registers and settings by the help of the user's guide, we'll be writing C code in Code Composer Studio for observing the multiple channel analog-digital conversion on the serial monitor. In our setup, we are going to be connecting 6 potentiometers to our launchpad and doing the analog to digital conversion of their outputs. We connect the VCC of the potentiometers to the 3.3 volt output of the launchpad, and we connect the grounds of the potentiometers to the ground pin on the launchpad. We connect the output of the first potentiometer to the P1.0 pin on the launchpad, leaving pins P1.1 and P1.2 blank. We are going to continue to connect the outputs of the remaining 5 potentiometers to pins P1.3 to P1.7 on the launchpad. The reason we are leaving P1.1 and P1.2 blank is that we are going to use these pins for digital communication and configure UART on these ports. However, we will not physically connect these 2 pins, since we will be using the USB connection on the launchpad as the communication port. Make sure that you connect the transmit and receive jumpers on the launchpad horizontally in order to use USB connection for serial communication. Now let's quickly see how the multiple ADC conversion is done in MSP430. In the MSP430 Family User Guide, literature number SLAU 144J, let's go to page 539 for conversion modes in ADC10 module. In our previous video, we had done single channel single conversion, and it was sufficient to constantly use the value of the ADC10 mem register in order to observe the single channel. However, in this example, we will have multiple analog channels, and we are going to repeat the conversion for this sequence of channels. And as we have only one single register ADC10 mem to hold the conversion results, we need to have some kind of a mechanism to record its value and the channel's ID at the same time in order to keep track of the values properly. For that, we are going to use DTC, Data Transfer Controller. Now let's see how the repeat sequence of channels mode works. In this mode, a sequence of channels is sampled and converted repeatedly. The sequence begins with the channel selected by the input channel X and decrements to channel A0. Each ADC result is written to ADC10 mem register. The sequence ends after conversion of channel A0, and the next trigger signal restarts the sequence. This means that for our setup, we should set the input channel as 7, since we are going to start from channel 7 and come down to channel 0. Since our P1.1 and P1.2 are for UART, the values we get for these channels won't be valid. So we are going to be in this loop until we reach channel 0, and then we trigger sampling again with rising edges for ADC10 start conversion and ENC, enabling conversion, so that the conversion restarts. As we see in this description, each ADC result is written to ADC10 mem. Now let's go to the Data Transfer Controller section to see how it's going to support us. The ADC10 includes a Data Transfer Controller DTC to automatically transfer conversion results from ADC10 mem to other on-chip memory locations. The DTC is enabled by setting the ADC10 DTC1 register to a non-zero value. So we are going to set the DTC value to 8, since we are going to require 8 transfers. We are going to be using the one block transfer mode. As we mentioned previously, we are going to set the ADC10 DTC1 to 8 as the number of transfers for a block. The internal address pointer is initially equal to ADC10 SA, which is standing for start address, and the internal transfer counter is initially equal to N. The internal pointer and counter are not visible to software. The DTC transfers the word value of the ADC10 mem to the address pointer ADC10 SA. After each DTC transfer, the internal address pointer is incremented by 2 and the internal transfer counter is decremented by 1. This means that after the first block, which is consisted of 8 elements, is finished, if we check the memory address that the ADC10 SA holds, we are going to see the conversion value of the A7 channel. If we go to the memory address that ADC10 SA plus 2 holds, we are going to see the conversion value of the A6 channel, and so on and so on. So if we create a dynamic array using this pointer, we can keep track of the results very easily, and we are going to do it by assigning the memory address of an ADC array to the ADC10 SA value as the conversion starts. Let me try to demonstrate what I'm meaning here. So we are going to be having an array. Let's name it ADC. And it's going to be consisted of 8 elements. After the first transfer, its first element, which is ADC 0, will be filled in by the value of the A7 channel. In the second conversion, its second element, which will be ADC 1, will be containing the value of the A6 channel. And it's going to continue until it gets the value for the channel A0. Now let's quickly jump to Code Composer Studio and see how we put all these together into C code. Before the main function, we declare the necessary character and integer values that we are going to use in the code. In line 23, you can see the array that we just mentioned of. It's going to hold the conversion results of the channels. In the main code, until line 36, we do the settings for the digital communication UART at 19,200 baud. If you take a look at the important differences we have for ADC multiple conversion, in line 38, with input channel 7, we set that the conversion starts from A7. With consec_3, we choose repeat sequence of channels. In line 39, MSC is an important setting for multiple sample and conversion. And in line 40, we define the channels that we want the analog input to be enabled. Make sure that you do not choose bit 1 and bit 2, otherwise the serial monitor won't work. And in line 41, we define the transfer block as 8. In the while one loop, we start the conversion at line 47. And in line 48, which is really important, we set the address pointer of the DTC to the memory address of the ADC integer array's first element, so that we can store the conversion values there. Between lines 49 and 56, we convert the integer values, which will change between 0 and 1023, to characters and send them to serial monitor to observe via the terminal. Between lines 61 and 66, we have our serial output function. Now let's run the code and observe the outputs in the terminal. Let's click on resume. And let's open the terminal window. You can see that we have started receiving the values from the analog to digital converter module. You can observe that we have 8 columns here. First one is A0, second one is A1, which is not used because we are using it for UART, and A2 is also not used, it's also used for UART. And in A3, we have the value of the second potentiometer. And in A4, we have the value for the third potentiometer, and so on. Now let's set all the potentiometers to the minimum value. Okay, now you can see on the screen that for A0, we have a value of 1, 2, or 3. And for A3, we have, again, values like 0, 1, 2, and etc. And for the rest of the potentiometers as well. Now our multimeter is connected to the first potentiometer, and we can observe the voltage there. So let's try to increase the voltage on it. As you can see, as we increase the value, we can observe it on our multimeter and also on the terminal as well. So a value of 775 is corresponding to a value of 2.5 volts. Let's increase it to the maximum level. Okay, we can have like 1013, 14 here. Let's observe the second potentiometer, which we are going to see it in the A3 column. We can observe the increase of the value. We are at around 990 and around 1020 levels. And I'm increasing the value for the third potentiometer You can observe it at A4 column. In A5, I'm increasing the value, A6 and A7. You can see that we can observe all the 6 values of the potentiometers. We can have multiple changes, first and last potentiometers, you can observe them. Second and fifth, we can observe the values on the terminal. In the second setup, instead of 2 potentiometers, we are going to connect the X and Y axis outputs of an analog joystick to connections P1.6 and P1.7. Theoretically, there is no difference between these two setups, so we will be using the same code in Code Composer Studio. One thing that I need to mention here is the sensitivity of the joystick that I'm using is not so good, and it increases or decreases the red value so fast as you move the joystick. So you'll go from the mid value, which will be around 500, to the top 1023 or the bottom 0 value very quickly. Using a better quality joystick may be a solution for this. Now let's observe how these values are read for the joystick. In the second setup, you can see that I've connected the joystick instead of the 2 potentiometers, and I've connected the ground to the ground on the launchpad, actually on the breadboard. You can see that there is a 5-volt connection here, but I connected to 3.3 volts as well, because it won't matter for the joystick. And I've connected the X-axis via the yellow cable to the A6 channel, and I've connected the Y-axis to the A7 channel. We will be able to observe them on the terminal. Now let's resume the code. Okay, we can observe the joystick outputs in A6 and A7. So as I move the joystick in the horizontal position, you can see that A6 has changed, and it is now increased up to 1000. In the original position, it's around 497. If I go to the left, you can see that we have reached 0 very quickly. If I try to move it gradually, I can have values like 230, 215, and so on. And in the Y-axis, we can see that as I move forward, I've directly reached level of 0, 1. And if I move backward, I've directly reached 1021. So you can see that the joystick is not so sensitive. So I'm trying to increase it gradually, 600, 800, 900, and so on. So we can see the change in both axes as well. So this was the end of the video. I hope it's been useful for you. If you have any questions or comments, please write them in the comment section. Thank you for watching, and see you in another video.